Now let's talk about linear algebra. And again, this is not comprehensive at all. It is actually a very brief review. So we're going to start from a scalar and vector. And scalar is actually a zero-dimensional quantity, okay, including integers and the real and rational numbers, etc. Something like 1 or 2 or 3.14. Sometimes we can use variables like a, x, y. So as long as they are zero-dimensional variable. And the next, a vector. A vector is one-dimensional array of scalars. And if you are familiar with C program language, then you know what I mean by this one-dimensional array. Okay, and the vector is actually we can use two different types of vectors. First one is column vector, and the second one is row vector. Okay, the shape is completely different. So column vector is the shape of column vector is d times 1, and the row vector is 1 times d. Okay, this one is actually one example of column vector. So this one is vector, and we have d elements, and actually this one is a scalar, and this one is a scalar too. So we have d scalar values as an array. So including all these numbers, x is a vector including d elements, and this one x is actually in d-dimensional space. And usually we use column vectors, not row vectors. So when I say a vector, usually most of the time it is column vectors. Okay, next, inner product and magnitude. So when we have vectors, then we can add. So we have x and we have y, so we can add two vectors to get z. So look at this figure. So this one is x, and we have y, then we can add to get z. Okay. So if z is x plus y, then y is z minus x. And next one is inner product. So there are a couple of different notations here. Sometimes, this one sometimes like this. Okay, so this one is transpose. And the inner product can be calculated in this way. So we multiply the elements. So something like this: x1 times y1 plus x2 times y2 plus etc. and xd times yd. And we sum them up to get one scalar value. So the result of inner product is a scalar value. Okay, next one is magnitude, usually a Euclidean norm. Okay, so this is the notation. And to calculate this magnitude, then we actually apply the inner product to himself, and we apply this root square operator. So element wise, we can describe this in this way. Okay, so far so good. And next, we can calculate the distance between two vectors. Okay, so there are many different types of distances. So in this slide, we want to talk about Euclidean distance, which is the simplest distance between x and y. So distance between x and y is actually the norm of the difference between x and y. Okay, so this distance can be defined in this way simply. So again, this one is a norm and this one is the difference. And as we have seen in this slide, the norm can be calculated in this way. Likewise, we square the element-wise differences and then sum them up, and we apply root square operator. That's it. So in this vector space, this one is x and this one is y, and this is x minus y. X minus y has a direction, so y minus x is actually the opposite, okay? And the length of this one is actually the distance between x and y. So from now on, whenever we talk about vectors, then you have to think about the vector space. So vectors are in vector space. So vector means usually when we talk about data samples, and data samples are vectors. When we talk about image, then image is a vector. When we talk about a speech signal, then the speech signals can be represented as vectors. And the words and sentences and everything could be represented as vectors, okay? So you have to be able to imagine how these vectors and data samples are located in the vector space. That's really important to understand the machine learning models. When we talk about distance, there are some constraints. Okay, first of all, distance is a function, okay? So a metric or distance function. This is actually a bivariate function. Bivariate means we have two inputs. And usually if we say like distance between x and y, okay, then we have two vectors here. So we have two inputs and output is a scalar. So from two vectors to scalar, okay, that is a bivariate function. That's a basic condition. And there are actual constraints to these functions to be a real distance function, okay? The first of all, it should be non-negative. So no matter what kind of vectors we have, the distance between two vectors should be non-negative. It could, most of the time it could be positive, but it could be zero, but not negative. Okay, then the second constraint is that if the distance is a zero, then the x and y should be the same thing, okay? So, if x and y, if the distance between this x and y is the zero, then x and y is actually pointing the same point in the vector space, okay? Maybe we might use different variables, but they are pointing the same point, okay? So the third constraint is about symmetry. So distance between x and y is the same as distance between y and x, obviously. And the last one is triangle inequality. Distance between x and z is smaller than or equal to distance between x and y, and sum and plus distance between y and z. Think about this one. This one is x, and this one is y, and this one is a z. So the distance between this one is always smaller than or equal to distance between this one and this one, okay? So it is longer than this, obviously, but sometimes it could be equal only when the y is in the middle of x and z. Here is x, and we have z, and this one is y. Then we can have this equality. Okay, then let's think about some constraints like a symmetry. So do you know the Google Map? And the Google Map, actually the distance is not actual distance mathematically. From my apartment to the office, there is a path, okay? And the distance between my apartment to the office is different from my office to my apartment. Because when we drive, there are kind of one-way path or something. Sometimes we have to take a U-turn or something. So technically, mathematically speaking, Google Map doesn't have a distance, okay? But in general, usually people say it's the distance, okay? So this is just mathematical definitions. Okay, and later we'll talk about KL divergence, which is kind of distance between two probability distributions, but technically that is not distance because that is not symmetry, okay? And in the previous slide, we talked about Euclidean distance, and we have actually p-norm distance, which is a generalization of Euclidean distance. If p is 2, okay, if this one is 2, then it is Euclidean distance. But we can generalize. P could be 1 or 3 or infinite. Okay. So let's talk about some examples of distance. So first one is Manhattan distance. Okay. Manhattan is a part of New York City. Okay. And it looks like this. I got this one from Google Map. And let's say we want to check the distance from this to this. Okay, then definitely we are not interested in this distance. Okay, so we are interested in this. So in the Manhattan, when I go from here, when I want to go to this, then I have to go. I have to walk 3 blocks to the east side, and I have to walk whatever, like let's say 10, okay, 10 blocks to the north side. So 3 blocks to the east and 10 blocks to the north. That's enough, right? That's enough to describe the direction. Or that actually describes the distance, 3 blocks and 10 blocks, right? So in mathematically speaking, the Manhattan distance is something like this. From this point to this point, we counted the number of steps in this direction, and we counted the number of steps in this direction, and we sum. Okay, that is Manhattan distance. And basically this one and this one and this one, they have the same distance basically. Okay, and there are another distances like a distance in graph. And distance in graph is defined between 2 vertices in a graph, and it can be defined as the number of edges in the shortest path. It's also called a graph geodesic. So let's take an example of Facebook. Okay, so we have some relationship between other users, and we can say, for example, we can say like, oh, I have my distance to Barack Obama is 5, which means I have one friend who is friend to another friend who is friend to another friend who is friend to Barack Obama. Okay, in that case, my distance to Barack Obama is 5. Okay, so something like that. That is graph distance. Or another popular and famous distance is edit distance or Hamming distance, basically the same thing. So edit distance between A, B, C, E, F, and A, B, D, E is 2 because we have to replace this one with D, and we have to delete this one. So we need 2 operations to make this string from this one. So we need 2 operations. That's why edit distance between these two strings is 2. So this is really popular when we work on the strings, like a DNA sequence, or when we work on actual words. Okay, then the edit distance is actually popular distance. Okay, and the reason why I talk a lot about distance is that distance is important. In machine learning, everything will be defined based on the distance. So if we define a distance, then everything is defined. I mean, one point cannot have its meaning without the distance, without the relationship with the other point. And the relationship can be defined by distance. Okay, so once we define a distance function between all the points, then we have a kind of structure of data samples. Okay, so it's really important how to define what kind of distance we use, how we define the distance between 2 points. That is really important in machine learning. So in the previous slide, we have talked about inner product between the vectors and the distance between vectors. So we have been talking about relationship between two vectors. And in this slide, we're going to talk about orthogonality between two vectors. Okay. So first, let's talk about the angle between x and y. X and y are two vectors. And given this triangle, then you know how to calculate cosine theta, right? So this one is the distance of the length of this vector, and this is length of this line. Then cosine is defined by this one and this one. So this one is a denominator, and this one is a numerator. Okay. So this one is a norm of y, so this is obvious. And how can we get this number? Okay, so let's say y can be decomposed into two vectors. Let's assume that x and y are in the two-dimensional space. Then y is actually y can be decomposed into two components, and like this. So this one is actually a unit vector in the same direction as x, right? So this one is a vector in the same direction as x, but the length of this one is 1. Okay. So this a is corresponding to this length, because y can be decomposed into two orthogonal vectors. So this one plus this one will be y. Okay. So this one will be a, and then we have another direction which is orthogonal to x. So this one is orthogonal. Let's say x0 is orthogonal vector to x. So let's say this one is x0. And then this one should be a unit vector too, which means the length of this vector should be 1, and we have component. Okay, so we can define y in this way, given x. Okay, then let's check y transpose x. Then x is orthogonal to x0. Actually, we are using this part. When x and y are orthogonal, then x transpose y is 0, and vice versa. So let's say x0 is orthogonal to x, then y transpose x is actually x plus x0 over x0 b and x. Okay, then since this one and this one is orthogonal, then we can cancel this out. So now we have this part. And then y transpose x is a times x square, right? So a is actually x over x y transpose. This one is actually this one. So we can get this number. So what I'm doing here is that the cosine similarity between x and y can be calculated in this way. Okay, so that's it. And as I said, and x and y are said to be orthogonal if x transpose y is 0. And x and y are said to be orthonormal, which orthonormal is composition of orthogonal and normal vector. So x transpose y is 0 and norm of x is 1 and norm of y is 1. Then x and y are orthonormal to each other. And the next thing is orthogonal projections. Orthogonal projection of y onto x. So we already talked about this a little bit in the previous slide. So given x and given y, when we project y onto x, so this one is actually projected vector onto x. And we know this length. This length is actually y transpose x over x, right? So this is the length of this vector. So this is actually a constant. And x, this one is a unit vector. So this one is actually this vector, right? So this is what this says. As I said, y transpose u1. u1 is, by the way, a unit vector in the same direction as x. So y transpose u1 is the magnitude of the projected vector, the length of the vector. Okay. Then let u sub 1 and u2 and 3 and the ud be the orthogonal unit vectors spanning the space. Okay. Then I'll explain what this means. Okay. Then y can be decomposed into this way. Okay. So spanning the space means these vectors are enough to represent any vectors in the space. So let me give you one example. So this one is a two-dimensional space, and this one is one unit vector. Okay, so one unit vector is not enough to span the space. What about this point? So this vector cannot represent this point. Okay, this vector can represent all the points on this line, or even on this line. Like this one is something like 3 times, let's say this one is u1, 3 times u1. Or this one might be like minus 1.5 times u1. So we can represent all the vectors on this line. But how about this one? So to represent this one, we need another vector, this one. This is orthogonal. So when we have two orthogonal vectors, u1 and u2, then this one can be represented by u1 alpha times u1 plus beta times u2. Okay, so then this one is, let's say this one, we are representing this one. Then alpha might be 1.2 and beta might be 1.3. Then we can represent this vector. Okay, so spanning the space means if we have these orthogonal unit vectors, then we can represent all the vectors in the space. So if we have a d unit vectors, then we can represent any vectors in the d-dimensional space. So these orthogonal unit vectors can span the d-dimensional space. Okay, good. And then any vector y can be represented as a weighted sum of all these unit vectors. Okay. And next slide is about the basis vectors. Actually, I already used some concept or notation of these basis vectors already. Let's say these vectors, okay, not orthogonal. They don't have to be orthogonal. So these vectors, actually, we have a vector sets. Okay, so we have n vectors, and they could be linearly independent. Okay, if they are linearly independent, it means none of the vectors can be expressed as a linear combination of the others. What does that mean? Okay, so we have a vector un, and we have weighted sum, and this weighted sum is 0. It means all the alpha n is 0. When any of alpha n is not 0, then this cannot be 0. What does that mean? Okay, so let's say we have a u1 and u2 and u3 in two-dimensional space. Okay, this one is u1, and this one is u2, and this one is u3. Then u1 can be represented as a weighted sum of u2 and u3. Okay, or u2 and u3, they can be represented as weighted sum of the others. Like u3 can be alpha u1 plus beta u2. Okay, so in this case, let's see, alpha u1 plus beta u2 minus 1 u3 is 0. Okay, so alpha is non-zero, beta is non-zero, and 1 is non-zero, but still we can have 0. But if we have linearly independent vectors in two-dimensional space, in this case we can have only 2 vectors. So in two-dimensional space we have 1 and we have 2, u1 and u2. We cannot represent u as weighted sum of u1. Okay, u2 is not on this line. u2 is not on this line, which means u2 cannot be represented by u1. Okay, so in that case, u1 and u2 are independent, linearly independent. So don't get me wrong, u1 and u2, we are not talking about statistical independence here. So we are talking about linear algebra, and u1 vector and u2 vector, they are independent, linearly independent. Okay. So in two-dimensional space, if we have 3 vectors, they cannot be linearly independent. There is no way. Okay. If we have 10 vectors in a 9-dimensional space, then they cannot be linearly independent. So again, if we have n-dimensional space, then at most we can have n linearly independent vectors. If we have a linearly independent vector set, then the cardinality of the set should be 9. Okay, n. Okay, and a linearly independent set of vectors can form a basis for a vector space. So they can span the vector space, and they can be used as a basis. if we have any vector x, then it can be represented as weighted sum of all these basis vectors. Okay, and we need the coefficients here. Okay, good. And then how can we get orthonormal basis vectors? Okay, here is one simple algorithm, Gram-Schmidt's orthonormalization process. So given a set of vectors, we can construct an orthonormal basis for the vector space. So given the linearly independent vector sets from x1 to xd, excuse me, orthonormal basis vectors u1 to ud can be obtained by this process. First of all, these are not unit vectors. So first orthonormal basis vector can be obtained by this. So just to normalize x1. So let's say we have x1, we have x2. So u1 can be obtained by this normalized vector. Okay, good. Then to get the second basis vector, orthonormal basis vector, then we have to subtract this x1 component from x2. Okay, so from x2, basically the second orthonormal basis will be the unit vector of t2, and t2 is based on just x2, but we have to subtract the component x1 component from x2. Okay, so we project x2 onto u1. Okay, so we project in this way, and we subtract all the component. So basically, we decompose x2 into these two vectors, this one and this one. And this one is on the x1 line, okay? And then we have another component here. Actually, this one is t2. Okay, and then u2 is this one. Okay, so in the two-dimensional space, I just showed you how to get two orthonormal basis vectors in two-dimensional space. If it is d-dimensional space, then we have to keep doing this again and again. In the third dimensions, let me tell you one more step. In the third dimensions, let's say we have another dimension, x3. And in this case, we have to subtract x1 component and x2 component from x3, and then normalize. That's u3, etc., etc. So td is based on xd, but we subtract all the components from xd, all the previous components, and then normalize. That's it. So as long as we have linearly independent vectors, then we can obtain orthonormal basis vectors.